Hi, welcome back. So in this video, we're going to continue our discussion with Riemann sums. And what we call the definite integral. Now notice, what's happening as the number of rectangles increases? Well, our delta x down here is going to get smaller and smaller and smaller. Delta x decreases. As the number of rectangles increase, delta x decreases. And that's what we get down here. How does the Riemann sum become the exact area? Well, as delta x, we want to find out what happens at delta x as the number of rectangles increase. And we notice it's getting smaller and smaller. If we let the number of rectangles n approach infinity, if we let this occur, we get this cool little thing. Delta x approaches 0. And our limit problem from yesterday, and our Riemann sum from yesterday now becomes a limit problem. The limit as delta x goes to 0. Remember, this is the area of my rectangle, length times width. And what we wind up is we change the notation. So instead of using a summation notation, we use what's called an integrand. This symbol right here is what we call an integrand. And what it's telling us is that this is a sum of an infinite number of rectangles. And something else happens. This delta x becomes dx. dx is the same as delta x. We saw this before with our derivative, dy dx, where dx is the smallest change in the x value as possible. And this symbol, this function right here is basically saying that this is the sum of an infinite number of rectangles. And it's going to give us the exact area under a curve. This is called and we call this a definite integral, and it is used to find the area between the function and the x-axis. We're going to spend a lot of time with this one next semester. So let's practice with some definite integrals. We want to use a left Riemann sum with 4 subintervals. In other words, remember, that is the number of rectangles that we want, to approximate the area underneath this curve. So we're saying we're going to let f of x be this x squared plus 1, and we want to find the area of that on 0 to 2. We really can't solve for right now because we don't know the area of a parabola, but we can use our Riemann sums from yesterday to help us. So the first things first, we got to find the change in of our x values. We're going to go from 0 to 2. So we're going to take that 2 minus 0 and divide it by 4, and we get 1/2. So when we set this up, from 0 to 2, we're looking at 1/2, 1, and 3/2. I'm using a left Riemann sum, and I'm going to plug it into my equation here. If I'm using a left Riemann sum, that's going to put me at 0. Well, if I plug 0 into my equation, I get 0 squared plus 1, which is just 1. At 1/2, now I'm using 1/2. If I plug 1/2 in, I'm going to get 1/2 squared, or 1/4 plus 1. Plugging in the 1, I get 1 plus 1. And if I plug in the 3/2, I'm using my left, I'm going to get 9/4 plus 1. Now, I'm going to do something different. Now, yesterday, you might remember, we said let the area equal f of x dx. We're not going to write it that way anymore. We want to approximate the exact area. So we're actually going to write it using our definite integral. We're going to write it this way. Our definite integral, the area, is approximately, and we're just going to do this again from yesterday, my delta x's here are all 1/2, so this is going to become 0 plus 1, or 1 times my width is 1/2, plus my other one, this is 1/4 plus 1 times 1/2, plus 1 plus 1, that's just 2, times 1/2, and over here, 9/4 plus 1 times 1/2. And you might be thinking to yourself, this is no different than what we did yesterday, and you would be exactly right. The only difference is in our notation. We're going to change our notation today. So let's do a midpoint Riemann sum with 2 rectangles from 0 to pi. So again, I got to find my delta x. So same thing here, f of x is going to be sine of 2x on the domain 0 to pi. So to find my change in x, I take that pi minus 0 divided by 2, and I get pi over 2. Setting this up, 0 to pi over 2 is in the middle. Now be careful, I do want to use a midpoint. This is going to be my two rectangles here. Don't know exactly the height, but it doesn't really matter. I have to pick the midpoint. Well, what's in between 0 and pi over 2? That's pi over 4. So my first one is going to be at pi over 4. So I'm going to use my function, and this becomes the sine of pi over 2 times pi over 4, which is pi over 2. What's between pi over 2 and pi? 3 pi over 4. And if I plug it in, I'm going to get the sine of, this becomes sine of 6 pi over 4, or 3 pi over 2. And to get my area, I'm not going to get area from yesterday. I'm going to write it as an integral. Sine of 2x dx is approximately, and now this rectangle, each rectangle is pi over 2 from yesterday. There's my delta x. There's my height. The sine of pi over 2 is just 1, so this will become 1 times pi over 2, plus the sine of 3 pi over 2 is negative 1 times pi over 2. And again, we got 0. We saw a question like this yesterday. What does that tell us is that between 0 and pi, sine of 2 pi looks like this. The areas are going to cancel each other out. Right there. All right. For number 3, now we want to do a Riemann sum of 4 rectangles between 0 and 2 of x cubed. And then we want to know, would this be an overestimate or an underestimate? So let's do the delta x first. Let's find our change in our width, our base of our rectangle here. 2 minus 0 over 4 is a half. So remember, this is the width of each rectangle. That's the width of our rectangles there. So if I set this up, we're going to go 0, 1 half, 1, 3 halves, 2. And I have my 4 rectangles. I really don't know what it looks like, but this is just for me anyways. I want to use a right Riemann sum, so I'm going to pick the number on the right, and that's 1 half. So I have to ask myself, we're saying f of x is x cubed, and we're on the domain 0 to 2. So if I plug my 1 half in, I get 1 half cubed, which is just 1/8. If I plug 1 in, 1 cubed is just 1. 3 halves becomes 27 over 8, and 2 cubed, that's just me, or just 8. 2 cubed is 8. So to write out our answer, our integral using a right Riemann sum is approximately 1/8 times 1 half plus 1 times 1 half plus 27 over 8 times a half plus 8 times a half. And there is our area. Don't simplify. We don't want that. That's just a mess to simplify. Don't even worry about that. All right. Very easy to do. All right, let's take a look over here. Number 4, now we're going to look at it from a graph, from a table standpoint. And we saw these yesterday again. Let f be a continuous function on the domain 2 to 14 and have the value shown in the table below. Use a right Riemann sum to approximate the area from 2 to 14. So to do something like this, they don't give me number of rectangles, so I have to use them all. So if I start setting this up, we start at 2, 5, 10, and 14. I want to write Riemann sum, so between 2 and 5, I'm going to pick the number on the right, which is a 5, which is 28. Between 5 and 10, that's going to use a 10, which is 34. And between 10 and 14, we use a number on the right, which is 14, and that has a height of 30, not drawn the scale. But what I want to point out here is the differences. Here delta x is 3. Here delta x is 5, and here delta x is 4. They don't always have to be the same. So you've got to be really careful, which is why, if you notice in any of my questions, I never factor out my delta x's. Okay, I did forget one part here. We'll talk about that in a second. So over here, if I want to evaluate my integral from 2 to 14, f of x dx, it's going to be about, look at the rectangle. The first one has a height of 28 and a width of 3. The second rectangle has a height of 34 and a width of 5. And the last one has a height of 30 and a width of 4. And that's going to be about our area. Now notice, remember, because what this is saying, this is the length of our rectangle, and that's the width of our rectangle. Now I did forget something on part B, number 3 up here. Would this be an overestimate or an underestimate? Well, let's look at x cubed. X cubed from 0 to 2 looks like this. And if I pick any number on the right, it's going to be an overestimate. So I know this is going to be an overestimate. But why? Well, to determine why, we have to go back to yesterday's note. One, this is an increasing function, and we're going to say that because f of x, f is increasing. And 2, we're taking a right-hand sum. There's 2 reasons for it. If this was a decreasing function, this would be an underestimate with a right-hand sum. So take a look at the notes from my video from yesterday, and you can see that more. All right, application. Bilbo went for a ride one Saturday. The odometer on his horse was broken. However, he still wanted to determine how far he traveled. Luckily, the speedometer on his horse was working. Bilbo made the following chart of his speed or velocity of the horse at certain times, and Bilbo traveled for a continuous 50 seconds. So the first question says, what is the meaning of the definite integral? So I want to talk about what a definite integral finds for us. We know yesterday, to get the units, I'm just going to multiply these together. This is going to be feet per second times my time. Whoops, let's make this also minutes instead. Let's fix that to feet per minute. Makes it easier. Times minutes. These are going to cancel each other out. And what we're left with is just feet. Well, how does our integral tell us? Well, that's what this tells me. The integral, or the definite integral, v of t is in feet per minute. dt is in minutes. Those cancel, and we're left with feet. So what this is telling us is, this is saying that the area, or the integral from 0 to 50, v of t, is the change. We call this a change in position. In position on 0 to 50 minutes. It's just telling us his change in position during those 50 minutes. Slow moving horse. Should be leaving for seconds. So now we're saying approximate this using a left-hand Riemann sum of 4 subintervals. So we have to get our change in x, or change in t in this case. 50 minus 0 over 4. Whoop. Really can't do it this way. So let me rephrase from here. Let me rephrase this one. We really can't do it this way and this one because they're not evenly spaced. If this is like because this is a table, we really can't find our delta x's will change. So I'm just going to set this up. I want to go for 4, 0, 10, 15, 30, and 50. These are going to give me my 4 rectangles. Very easy to do. Between 0 and 10, we want to use the left. That puts me at 5. Between 10 and 15 puts me at 8. 6. And between 30 and 50, we're going to be on the 30, which is on the left, which is going to put me at 10. So I can approximate this. 0 to 50. V of t dt is about 5 times 10 plus 8 times, remember each one of these is different, right? 8 times 5 plus 6, this is now 15, and then 10, and that's 20 times 20. Remember, the length of my rectangle and the widths of my rectangle, that's my dt's there. And what's the unit? We already said this is going to be feet. So this is saying that this is how far the horse traveled in those 50 seconds. Using a midpoint of 2 subintervals, midpoint sum, same thing. 0, 10, 15, 30, 50. Well, I only want 2 rectangles, so I'm going to split it in the middle here because that's going to give me 2 rectangles, which is nice because now I got these nice little midpoints here. They're not exactly the midpoint, but they're in between the 2. And at 10, we know the height is at 8, and at 30, the height is 10, so I can approximate it this way. and that's going to give me 8 times 10, 15, that's terrible of me, plus 10, and this distance right here is 35. And again, feet. And there's our answer right down there. Sorry about that, you can see that. Oh man, it's terrible. This height is 15, and this thing right here is 35. Sorry if you can see that, I'll leave that up there for a second. I hope you enjoy the videos, and I'll see you later. Bye-bye.